Hello, everyone. I'm Assistant Prof. Gary Lei from the National University of Singapore, and here I'm visiting Venus for 1 week. So my background already introduced very well, and I think I would just like to add on that my field is called environmental fluid mechanics. So it is about to studying the fluid mechanics between vegetation and water. And the vegetation I study include a wide range. So I study seagrass. um, So I study seagrass, I study mangroves, coral reefs, kelp, and etc. And today my topic will be about physically modeling nature-based solutions for coastal protection, and insights from seagrass mangrove. So the previous presentation was about the nature-based solution for the soil and civil infrastructures. My focus will be slightly different, and it will be about the water and how nature-based solution reduce the water energy or the wave energy. And the QR code is my personal website, also my lab research group's website. If you want to look into more details, please feel free to scan the QR code. I also show the same code at the end of my presentation. Okay, next slide. So my experience is already introduced. It's in environmental fluid mechanics, and then for most of my work, I will do lab experiments. So I will be showing you some of the lab experimental results. I also do a little bit of field experiment and numerical simulation. However, I tend to be keen to collaborate with modelers and field experimentalists, such that we can combine each of our strengths. So if you're interested in my study, and if you happen to be a modeler with field experimentalists, so I'm very happy to collaborate with you. So next one. Coastal habitats, it is the intersection of land and sea, which provides a unique environment and habitat for biodiversity to thrive. So here we can see that we have mangroves, seagrass, salt marsh, and coral reefs. And now, within the decade, people are getting more and more interested in nature-based solutions. And in 2015, there is a Nature paper talking about the integration of nature-based solutions such as salt marsh, oyster bass, seagrass, barrier island, etc., to coastal protection. And from about 10 years ago, people are getting more interested in using nature to counter the wave attack and to protect our coastal lines. Now, here I just want to show you that the motivation for this study. So at the upper right corner, you can see a coral reef photo taken at Bali, actually, from one of my students. And then the lower right corner is a mangrove and rock rewetment. And this aligns with the previous question that is it possible to combine hard structures or the non-nature-based solutions with the nature solution? This is one of the hybrid solutions in Singapore. So the motivation is that nature-based solutions are becoming increasingly important compared to traditional hard structures. The nature-based solutions have co-benefits. Okay, so it says the slides are not showing up. Can you see my slide? I think it should
I
be.
can't see the slide.
Oh, okay.
I think
So
the settings maybe.
okay. But compared to traditional hard structures, nature-based solutions have co-benefits for community, and it's also shared by the previous prof, and they're adaptable to sea level rise. Now, the existing effort, so what we have already studied and what people already understood is for the coastal protection benefit, it is the attenuation of waves and current under simplified flow conditions. Basically, people have done a bunch of studies under simplified flow conditions to quantify how much wave energy or how much flow velocity can nature-based solutions reduce. Now, by simplified flow conditions, I mean it is the simplified vegetation morphology. For example, sometimes we use
Sorry, Gary.
Yes.
Your PowerPoint is not showing yet.
A slide is not showing.
Not showing.
Yeah, really?
Yes,
Okay,
I cannot see your slide.
maybe I reshare. Okay, hold on.
Maybe you should redo your presentation share screen.
How about now?
Oh, yeah. Content shared by participants only visible to host and co-host.
Can you see my slides now?
Wait
No.
a second. Wait a second. I think
Jadi fokus aja dulu. Nggak bisa ya. Focus mode is ending. Oh, ini baru. Karena focus mode. Udah bisa.
Oh, it says my share screen can be seen only by host and co-host. Is that the settings?
I think it should be fixed by now.
Oh, yeah.
Okay.
Now it's everyone.
okay.
Okay, yeah, thank you. Okay, I think just the setting issue. Okay, so let me just quickly just show you the slide I just went through. This is the introduction slide for nature-based solution for coastal protection. And now I'm talking about existing effort. So by simplified flow conditions, first of all, it could be the simplified vegetation morphology, which is shown by the image that you can see at the lower right corner. Sometimes people use rigid cylindrical wooden cylinders to represent mangrove roots. And they do look similar, however, it's a simplified morphology. And people also do studies on uniform distributed elements, which means that the nature-based solution element or the vegetation are uniformly distributed. However, we know in the real world, they're probably not uniformly distributed. Some place may have more and some place may have less. So to model these mangrove roots and seagrass in the lab, we would use something that looks like this. Okay, so on the left side, you can see to model the mangrove roots, we use wooden cylinders. On the right side, you can see to model seagrass, we use this artificial plastic seagrass blade. So now I want to move on to the fundamental science in nature-based solution and how nature-based solution work to reduce the flow intensity and then the wave height. So now I want to do two cases because there are two distinct types of flow. The upper one is called the waves, which means the flow that you see when you're standing on a beach. You see the wave going back and forth. You see the wave peak propagate towards you. And the other type of flow, as shown at the bottom panel, it's called currents. And currents basically represent rivers, streams, creeks, and all kinds of one direction flow. So let's look at the waves first. So if we follow the animation, you will observe that the wave height, which is the distance between the wave crest and the trough, decreases as the wave propagates through the meadow of vegetation. So now people have already had a good understanding of how much wave height can be reduced. And this formula is developed by Dalrymple in 1984, okay, 40 years ago. So we have this formula, and then that quantification depends on a bunch of parameters, including the radiant frequency or the pure rate of the waves, the amplitude of the waves, the wave number, the drag coefficient, the water depth, vegetation height, and the vegetation width. So by knowing the wave conditions and the vegetation properties, we are able to quantify how much wave energy will be reduced through the nature-based solution or through the vegetation. Now, not just the wave height will be reduced. So if we follow the particles denoted by the yellow dots, and then also the black curves, which denotes turbulence. So when you follow these in the animation, you will also find out that because of the wave energy is reduced, sediment, which is denoted by these particles, will tend to settle down after passing through the vegetation because the flow intensity diminished. So nature-based solution can also suppress sediment resuspension and prevent erosion. Now here, I want to introduce another type of flow, which is, if this current one direction flow, it can be tidal current in the estuaries. It can be longshore current in the beach. It can be rivers. It can be creeks in the inland region. So again, please follow the animation. So before the flow reaches the vegetation, we can generally assume that the one direction flow is uniformly distributed across the water depth. So you can see it's a relatively uniform distribution, only near the boundary is smaller because the boundary layer theories. But if you follow that, as the flow develops through the vegetation, you can observe a redistribution of the flow speed or velocities across the vertical profile. And here you can find out that within the vegetation, the velocity is reduced. However, above the vegetation, the velocity is increased. And this is because the drag forces acting on the vegetation elements, and that drag force will have blockage impact, and that will reduce the flow velocity. And due to continuity, within the vegetation, the velocity is reduced. So above or outside the vegetation, the velocity or speed will increase. Now, again, this is theory for quantifying the degree of this redistribution of velocity is proposed by Chen et al. In 2013. So this is about 10 years ago. We have the theory to do the estimation. All right, so these are the basic signs of nature-based solutions. However, there are some things that people have not understood or have not studied, and that includes the efficacy of nature-based solution, first of all, under realistic three-dimensional flow condition. And I want to highlight here, this will be the topic or the detail I would like to introduce today. And why this is important is because when we think about a shoreline, for example, the Indonesian shoreline, the South Jakarta shoreline, that it can be very long. And when waves hit the beach, usually it will be at an angle, and that waves can generate a flow that is parallel to the beach. So as well, you can see on the right side, when you have an incoming waves that generate the longshore current, and these two flow combined will be a three-dimensional flow. And this is hardly studied by anyone in the world because it's too complex. Again, there are the other knowledge gap is that to study the impact of non-uniformly distributed nature-based solution. And one example I want to give is on the right side. You can see that part of this lab basin is vegetated and the other part is unvegetated. And this is also something that has not been understood very well. And if the unvegetated region can be protected by the nature-based solutions or not is a question. And then some other knowledge gap will be to understand if we can integrate the nature-based solution with non-nature-based solution, also consistent with the question asked previously. So we call that the hybrid solution, which is the green components, the nature-based solution element, plus the gray component, which is hard structures like concrete, seawalls, revetments, dikes, and etc. And lastly, real vegetation is also very difficult to study because of this complexity and the real morphology. Now, the research question, or the research result I want to introduce today is about the first knowledge gap, which is to understand the realistic three-dimensional flow condition I'm actually working on all of these knowledge gaps, but for the time constraint, I'll only show you the details for one. If you're interested in others, please let me know through email. So the research questions will be how to characterize vegetation in these complex three-dimensional flow conditions. And then what is the impact from an additional orthogonal current, which represents the longshore current, to the drag force that experienced by a single vegetation blade. So to answer this research question, first of all, I want to give a sort of a more detailed explanation of how the forces will be acting on the vegetation elements. I'm going to use seagrass as an example. So seagrass is one kind of flexible vegetation, as what you can see here. So the bottom part, the brownish part, are the rhizomes and then the sheath. Okay, and the green part are their blade, which is above the ground. So the brown part is below ground. And you can imagine if there is a flow passing through, because they're flexible, they will bend. And if the flow is more intense, they will bend more. If the flow is less intense, then they will bend less. And then to look at the forces that acting on these seagrass element or seagrass blades, we will first look at the drag force equation. So for a drag force acting on a rigid structure or a rigid object, or a rigid blade, the force or the drag force can be simply calculated as 1/2 times the density of water times the drag coefficient times the blade width times the blade length times the flow velocity. Okay, so this is the classic drag force equation that in fluid mechanics courses you should all be seeing this before. Now the question is, if the blade becomes flexible, if we are looking at the seagrass blade, what the drag force should be. So in my studies to understand how to characterize flexibility of vegetation, I introduced a concept called the effective blade length. So here, the length of the blade is L. However, when it bends due to flexibility, the drag force on a flexible blade can be expressed using a very similar expression with only one difference. And here what you can observe is that the blade length L is replaced by the effective blade length L sub E. Now, L sub E or LE here, it is the length of the blade of a flexible blade. That is basically effectively how much force is acting on it. So in our modeling or in our conceptual design, this flexible blade with length L is equivalent to a rigid blade with length LE. Okay, and usually this effective blade length is smaller than the original length. For example, the original length can be 20 centimeters. However, it bends by this much, and effectively the length is 10 centimeters. Okay, so basically that will just be the concept of this effective length. Now, for the wave properties, here I just want to introduce the linear wave theory, which is just a widely used theory for the quantification of wave speed or wave velocity. So here, the wave particles, so under waves, water particles move following an elliptic path. And then the wave velocity depends on the position it is at the water column. It depends on the period of wave. It depends on the wave height or the wave amplitude, the wave number, and the water depth. And then, so what we can see here, so this is the wave crest illustration. And then later on, this is the wave trough, which meaning when the water level becomes the lowest and the trough of the wave passes through. Now, an important concept I want to introduce here is called the wave excursion, which is the radius of a wave orbital, which that represents the length that one water particle will travel within one wave cycle. As I mentioned before, water particles, they follow an elliptic path as denoted by the dashed lines. So the radius of this dashed line will be the wave excursion AW, and we'll be using these concepts later. Now, as I mentioned earlier, we want to quantify the flexibility of vegetation. And then in our studies, we find out that there are two parameters that are very important to determine how much the flexible vegetation bend. Now, the first dimension is parameter is called the Cauchy number. We use Ca to denote the Cauchy number, and it's the ratio between the drag force and then the restoring force due to blade stiffness. So here you can see in the numerator, we have this drag force expression, and in the denominator, we have the modulus times the second moment inertia, which represents the restoring force due to stiffness. So what this value means is that if this is high, if the Cauchy number is high, meaning the drag force is much higher than the stiffness, the flexibility will be very significant, and the blade will behave as if it's very flexible. This is what you can observe from the illustrations at the bottom half of these slides. So when the Cauchy number is about 4,800, the blades are very flexible. When it's smaller, like about 3.8, it is more like a cantilever beam. And when the Cauchy number is only 0.1, it almost doesn't move at all. Okay, and next, we also have the another parameter which represents the waves, and we call this the blade length ratio, and this is the ratio between it's a ratio of blade length to the wave excursion. Wave excursion is what I mentioned earlier. It's how much a water particle moves during a wave cycle, and the blade length just means how long the seagrass blade is. Now, also from the illustration, you can find that two distinct cases. But first of all, if this value is smaller than 1, that means the blade with seagrass is very short. So it cannot follow the whole wave cycle, right? So when wave passes through, the wave or the water move much more than the seagrass. So the seagrass will be bent at the most bent position, and then will just stay there, and it will only come back when the water particles come back. So you cannot follow the whole wave cycle. However, if this blade length ratio is greater than 1, that means the blade length is long enough such that it can follow passively with the waves. So this will be about the two important dimensionless parameters. And from dimensional analysis, which is also dimensional analysis developed by originally developed by Alban in 2002, that the scaling law that can quantify or to quantify the relationship between the effective length and these two-dimensional parameters is as follows. So we use dimensional analysis to link the drag force, which is the formula that you can see on the left side, rho CD BLE UW squared. And then on the right side of the formula, it is the restoring force due to stiffness, EI times the second derivative of theta respect to the distance from a distance along the blade. Now, from this dimensional analysis, researchers have found out that the effective length ratio, which is the effective length normalized by the original blade length, scales as the product of these two dimensionless parameters, Ca times L to the power of minus 1/4. Okay, so, and for pure waves, here I just want to give you a flow map so that you have a, to summarize all I have talked about. We have the scaling law, the normalized effective length scale as Cauchy number L to the power of minus 1/4. And we have the definition of two-dimensional parameters also in the text box. And on the right side, just an illustration of the original length and then the effective length. Now, this scaling law could be more complex and complicated if you have a three-dimensional flow. So what I have shown earlier will be about pure wave. If we only have waves in a two-dimensional domain, this will be the scaling law. However, if you have a current, where you have a one-direction flow, a cross current that is perpendicular to the waves, that scaling law will be different, and this is something we are trying to understand. So here, so here I list 4 regimes for the different scenarios for these three-dimensional flows. Now, what we do not understand is when the cross current is comparable to the waves. When both directions are important, we have to figure out if the scaling law, the minus 1/4 scaling law, still works in this regime. Okay. Now, of course, our hypothesis is that this scaling law of Cauchy number L to the power of minus 1/4 still work in this regime. And the only thing we need to replace would be to replace the Cauchy number, which represents the ratio of the drag to the blade stiffness. So we know that if you have a cross current, the drag force will be enhanced. So here, well, you can see that in the Cauchy number, we also change the expression of the numerator so that we made changes to the formula, and we propose that this change can yield the same scaling law, and I'll be showing you some results very soon. So here, to study this behavior or the scaling law, we did lab experiment. So this is one of our lab facilities. This is a wave basin that is 24 meters long and 10 meters wide. And we can see that we have the wave paddles these blue ones, they will going back and forth and generate some waves. And the cross current is generated from here. There is a reservoir, and when we open the tailgate, there will be a cross current that is in the direction that is perpendicular to the wave. So we have a three-dimensional flow. Now, this is our setup for measuring the forces. So on the bottom left corner, you can see we fabricate a pyramid to serve as a holder or ramp for the force sensors. So the force sensors are mounted below the vegetation blade or the seagrass blade. And then at the bottom right corner, you can see this is our artificial seagrass blade, which are basically a silicon rubber rods that are flexible and that dynamically represent seagrass because they have similar flexibility. And we have the vectrino to measure the velocity, and we have the wave gauge to measure the wave height. And there are cameras, 2 GoPro cameras, one looking in the direction of the waves and the other looking in the direction of the current to quantify the motion of these flexible objects. So, and these are some experimental parameters. So we have water depth is 30 centimeters. The wave period is from 0.2 to 2 seconds. The wave height 6 to 12 centimeters. The blade material has a modulus of 5.24 or 0.96 MPa. And the blade length 9, 14, and 19 centimeters, which also represents the range of the seagrass in Singapore. Okay, so the results, I would like to show you the forces on an individual rubber rod or an individual artificial vegetation element. And the other result I want to show is the scaling law validation. And we are going to see if the scaling law still works for pure wave and combined wave current conditions. Now here is the first set of results, which is about the forces on an individual flexible seagrass blade element. So left side is their motion. So we have, so this shows you the motion of the blade at different different conditions. Now the hex bar here denotes the length and the flexibility of the blades. So the upper one is the most rigid one, and then the bottom one is the most flexible one. We can clearly see that when the flexibility increases, the range of motion in all directions increases. So the first column is the pure wave conditions. If we only have waves, this will be the range of motion. And then the second column is the combined wave currents, three-dimensional conditions, but in the wave direction. And the last column is the three-dimensional wave current condition in the current direction. So, but for all of these columns, you can observe that the last one, being the most flexible one, will have the largest or the widest range of motion. And then on the right side of this slide, I'm showing you the forces on an individual element. So the first two plots are the forces within one wave cycle. So the dashed line is the force on a rigid reference blade. The red one is the force on a blade in pure waves, and then the blue one is the force on a combined wave current with three-dimensional flow conditions. So what we can observe here is that the forces are actually quite similar for the two-dimensional wave and the three-dimensional wave current conditions. However, whatever for both cases, you can find out that the flexible forces, which is the solid lines, are significantly lower, has a significantly lower magnitude compared to dashed lines, which represent the force on rigid structures. Now, the last plot on the bottom right corner shows you the comparison between the forces in the two-dimensional flow conditions versus the three-dimensional flow conditions. And you can see they're not that different. So within uncertainty, I think they have good agreement with each other. So the conclusion from this force measurement is that, first, the difference of the total force that acts on a single blade is insignificant between the two-dimensional pure waves and then the three-dimensional orthogonal wave current conditions. Secondly, the blade motion increases with longer blade length and smaller flexibility. And the higher flexibility, sorry, so that will be a typo. A smaller range of motion contribute more drag force due to large frontal area relative velocity. So if we have smaller range of motion, there we observe the more forces acting on the blade. Okay, so the other result I want to show is the validation of the scaling law. So here I'm showing you the scaling law in all different cases. So on the left side, the y-axis is the normalized effective length, LE or L, and the x-axis is the product of two-dimensional dimension is prime the CAL. And then the dashed line, the solid line, represents the scaling laws. The solid line is just the scaling law to the power of -1/4, and then the dashed line is a fitted scaling law with the same, the fitted scaling law. And what you can see is that for both the two-dimensional wave conditions, which is the first plot, and then the three-dimensional flow condition, which is the second plot, the data follows the scaling law, follows the -1/4 power decay in all the throughout all the cases. And so what this suggests is that now for all of these conditions, the scaling law normalized effective blade length is scaling with Cauchy number L to the power of -1/4. This applies well for orthogonal wave current conditions. And what you can also observe is that the higher magnitude of the experimental data, it can be so attributed to the neglect of varying inertial terms and buoyancy forces in the expected scaling law. So basically what you can see is that our fitted scaling law, which the red dashed lines, are always higher than the theoretical ones. I won't say theoretical ones, but it's the scaling law developed earlier by other studies. I think this is because our morphology of the blade is a cylindrical structure, but for the solid black lines, they use flat plate. So we believe that the difference is due to the fact that we did not consider the inertial forces and the buoyancy forces, which we'll be trying to figure this out later. So in the last part, I just want to introduce you how we can apply our theories. So first of all, we can extend the effective length theory to predict wave attenuation over a vegetation meadow, which means an array of vegetation elements. So here you can see this is basically showing you the study of the wave decay over an array of vegetation elements. Okay, and so here this is just also showing you we already done something about the wave decay over an array of vegetation elements. And here is some experimental setup I want to show in our lab that we have these rigid cylinders to represent mangrove roots, as what you can see on the left side. And then this will be representing the real mangrove roots in the field. And we study how much wave energy this can help to reduce, to protect the coast. Now, lastly, I just want to show a video, and this will be a drone footage to showing you the experiment that we're doing in our lab and how we measure the wave height. How we measure the wave height decay through the vegetation. You can see we have waves generated by the wave paddles. And then we have this vegetation patch, which consists of 12,800 artificial mangrove roots. So basically the wooden cylinders. As wave passes through, we'll have sensors to measure the wave height, and we measure it across the whole domain of these 12,800 cylinders to understand how much wave height is decay and how much wave energy is reduced. Okay, let me maybe make this faster. Okay, so this is our lab. We have other flumes too, and we also do other studies. Okay, so here I would like to end my presentation today. And please let me know if any questions